Okay, the sound. All right. Good. All right, so let's start. This is where we ended last time. We're trying to finish the story about the measurement and then to continue with the sort of fault tolerant stuff. And today, all right, so I wanted to discuss, I guess, two things. One is somewhat error mitigation aspect, but not too much. And then also the aspect of how to construct some useful unitaries. Now, to sort of reiterate, in the measurement problem, we have these three aspects. First, on a classical computer, you need to do all these optimizations, partitioning, and finding the transformations. Then there is a unitary quantum cost, meaning that wave function that you want to measure, you want to put the unitary that diagonalizes the fragment. If it's a measurement using the some sort of fragmentation, and then do the measurement of z's that allows you to construct a polynomial here, the i's and polynomial. Okay, so that definitely extends the circuit, and in the near term, it turns out to be a big problem because fidelities of transformations of the gates that we use, they are limited, they are not one. So by fidelity, I mean roughly the overlap of what you would expect, kind of absolute value of the overlap of what you would expect function sort of ideal and function which is real, right? So this quantity after the gate is measured in numbers of nines because it's not usually one. Ideally, it would be nice if it's one, but usually it's either 0.99 or 2 nines, at least 3 nines, 4, so on. Current architectures, I believe we are not, we have 2 nines and at best, and 3 nines is yet to be achieved. Yeah, but okay. And then there's something that we mostly focused non-unitary quantum cost, which is measurement, and that we're trying to optimize. And interestingly, this story about the measurement is a story of optimizing the wrong quantities. It seemed to me because initially we were thinking about optimizing the number of fragments. That was incorrect because after all, it's one would practically kind of worry more about the number of measurements. And when we start optimizing number of measurements, we realize only later that, okay, you could do really great things with some complicated unitaries, but eventually, if your unitaries are too large here, you start getting the noise from the unitary, and you lose all the accuracy essentially, right? So that's why it's kind of a deal breaker. And we need some sort of, well, ideally error correction, but in reality, error mitigation. That's something that currently is used. There are multiple protocols, and here what I first put is that things that we discussed, qubit-wise commuting, Fourier commuting, and fermionic transformations. How many actually extra gates do we need to put for each of these methods? And you could see that qubit-wise commuting, it requires only a single qubit Cliffords. So namely, if you need to measure a particular Pauli, which is a product of X, Y, Z, and then if essentially you could say that I want, I'm facing the problem that either transforming X to Z or Y to Z because if in Pauli we have Z or identity, then we could measure without doing any extra work. And so this transformation is simply Adamar XH equals to Z. And this transformation is on top of Adamar, all you need is to add S phase gate, then you can get HS, say this Z. And so those things can be easily checked. Maybe actually the stuff I wrote here requires changing either order or the dagger, because but it's easy to check, since also depends on how you define Y. Is it I minus I, the other way of putting the signs? So, but generally this should work. One of the combinations probably will appear in the next homework to do this explicitly. Anyway, so as you can see, both Adamar and phase is Clifford gates, and yeah, essentially, if you have even Pauli product that requires for every qubit one of these transformations, so it's not more than a constant number of single qubit gates, and they are the cheapest. Also, they are Clifford, so it's kind of simple. Now, if we go to the fully commuting, we need more Cliffords, and this quadratic more divided by log, but technically still quadratic in number of qubits. And that number, I guess, I will not go into. There is some standard text from computer science literature which derives this scaling, and normal codes like Qiskit and others essentially have encoding of the transformations for fully commuting Paulis, so that we could do transformation into these. Today I will show some of the math behind how, if we have say x1, x2 plus z1, z2, so they are not qubit-wise commuting, how do we transform them using these Clifford transformations into say something like z1 plus z2, right? That would allow us to measure. Okay, and then the fermionic, even more expensive. They are done by so-called Givens rotations, and eventually you end up with a square number of 2-qubit Clifford gates. And some of the plots that one can build here is if we have fidelities starting from ideal case 1 and go into the say situations where the fidelities are first essentially end up with just 2 nines, then the variances of estimator, they grow, and here the color code, the blacks are the qubit-wise commuting, the blues are fermionic, and so technically the message here is that we have situations where fermionics are good for the ideal case scenario, but when the fidelity kind of getting worse, then qubit-wise commuting could be even better, right? In terms of the variance, in terms of the number of measurements you need to do, simply because there are lots of noise effectively will occur, and that will spoil the results, right? So that's the basic idea. And then there are also why we have only like multiple curves here. There are various error correction, error mitigation, techniques, which I would like to discuss next. So, all right. So now, what can we do? Essentially, there's there is something that we can do that is based on the fragments that we create, and there is something that we can do just in general, no matter what fragments we are considering. So one of the most, I guess, simple or not, one of the most straightforward, I guess, way of doing the kind of error mitigation is to recognize that, okay, if something happens to the function that you prepare, well, before the measurement or during the measurement, sort of, so you want to detect that the error happened, and if you are able to detect that, then you can throw out the result that corresponds to the essentially situation with the error, right? So you want to sort of be able to see the symptom of the error yourself based on the results of the measurements, right? For that, what we can use is symmetries. But when it comes to symmetries, kind of a little bit tricky subject. One can define the symmetry as anything that commutes with Hamiltonian. But this is very kind of poor definition of symmetries. First of all, because any power of the Hamiltonian will commute with Hamiltonian, right? So it's not kind of very helpful, even though we have a lot of potentially symmetries. So usually symmetries is something that is more restrictive. It's some operator that or set of operators that are kind of simpler to work with, because well, technically we want to work with them, as if we know that the Hamiltonian commutes with something simple, then all the eigenstates of the Hamiltonian, they are also eigenstates of the symmetry operators, right? Could be made. Okay. Now, but in this case of selecting the result, which sort of consistent with symmetry, the story is a little bit more complicated, because what you, let's say, if you are trying to get the eigenstate of the Hamiltonian in the VQE, that's the idea, but you're always working with some approximate state, and which is not an eigenstate of the Hamiltonian. The fact that the approximate is not exact doesn't disvalidate this approximation. But okay, then you want still the wave function to be, and that the one that you work is an eigenstate of the symmetry operator, in order to say that, okay, if something happens, the error happens, then the idea is that you identify that error occurs because error operator, let's say E operator, ER, modifies the function, so that now this function is not anymore eigenstate of the symmetry, and that is one way to detect that the error occurs. But also, you should be able to measure the symmetry in order to do this distinction, right? So that is essentially the second line there. The symmetry operator becomes O Z after transformation with the one that we apply to measure some fragment, right? So you construct your approximation to the eigenstate, then you do this unitary transformation to measure fragment, and then what you obtain at the end here are ZIs, and technically, in order to distinguish state of the right symmetry from the wrong symmetry, your symmetry operator needs to be presentable as UN as well polynomial of some zi essentially un. Right, so the same way our hn was presented, maybe polynomial is different, but the unitaries they need to be able to essentially formulate symmetry in terms of only z operators. Okay, if that is not going to happen, if symmetry contains if the symmetry operator after applying the unitaries this way contains the z part plus non-z part, well then you cannot really know what the symmetry eigenvalue would correspond to for the system that you are measuring, right? So you won't know. This state may be perfect state with the right symmetry, but you just cannot say anything about the symmetry operator because you cannot measure it. Okay, and so that is somewhat a problem with especially complicated symmetries like a square operator. For a square operator, and if you write it in a second quantization, it's a 2-electron operator, and there is not a simple unitary that will diagonalize this operator. So, needless to say that the symmetry, the unitaries that we use, they are not gonna be able to measure S squared. Then I guess other operators which are like say number of electrons for SZ, they are simply this one is number of electrons alpha plus number of electrons beta. And this one is just the difference between the two. So these are easier, but in general, they are still can be easily broken by if you go to the, let's say, qubit space, fully commuting techniques, which look at the Paulis of the fragments and group the Paulis based on their commutativity, the n commutes. So based on the commutativity, if you select the Paulis, you could easily select Paulis that in order to sort of rotate them into the z basis, they will break the, like these rotations will break the number of electrons, right? So as again, simple example would be just the case that we already looked at. This type of operator, it could be thought as a fragment, valid fragment to measure. But because this operator itself is not really something that commutes with a number of electrons, then it's easy to show then that that unitary, if you have a z1 plus z2, you dagger for this operator, then these guys will commute with number of electrons, but the unitaries will not, right? And so technically what will happen in this case is not like when we put the symmetry, well, essentially what will happen then is that these unitaries that we need to diagonalize the Hamiltonian, they are not gonna make number of electrons to be all z's, simply because in Jordan-Wigner, the number of electron is already like sum of z's divided by 2 number of electron, number of orbitals, and divided by 2 minus something of this kind. And then if you apply the unitaries that will transform x to z's, that those unitaries will transform some of the z's to back to x's, and so then there will be non-z part, right? So that's why generally fully commuting operator fragments, you cannot simply measure number of electrons Another way to think about this is that the unitaries essentially break the symmetry of whatever function you prepare, and that then you cannot really claim that if you find that after the measurement that the number, essentially you cannot say that you can measure the number of electrons after that, unfortunately. And then let's say, what can we measure? Like where can we measure, say, number of electrons? One can ask this question, or is Z. So the transformations that or the fragments that will allow you to measure number of electrons is the fermionic fragments, and they're the unitaries of the fermionic fragments, always written as a product of this that PQ a dagger P AQ minus Hermite conjugate version P point Q, and so all this will commute with the number of electrons, simply because they contain the same number of daggers and non-dagger quantity, right? So there is another more algebraic way of stating the same thing. It's like if you remember from the angular momentum algebra, like sigma x, sigma y, sigma sigma y, sigma z, they have well, in this, I guess 1/2 is not a good example. Maybe just a general algebra of the angular momentum, jx, jy, jz. There is an operator that commutes with all of them. It's a J² operator. And since these guys form the Lie algebra, SU2, in the Lie algebra literature, there is a such notion as a Casimir operator. That is a polynomial of Lie algebra elements. Indeed, J² is the Jx² plus Jy² Jz². It's a polynomial of these guys that will commute with every element of the algebra. And so it turns out that the number of electrons is commuting with these unitaries for the same reason, because these products here, they form also Lie algebra that we generators are like this, excitations, right? And it turns out the number of electrons is always a Casimir operator, the same. It plays the same role. It's just a linear polynomial for any function of EPQs, or any function with the products where that number of daggers and the number of non-daggers are the same. So for that functions, the number of electrons always will commute. Okay. So therefore, these fermionic transformations allow you to sort of do the post-selection for the function, considering again the situations where functions prepared with again with some fermionic rotations, or the one some unitaries that conserve number of electrons, right? Okay, and now, yeah, so the more complicated operator, the harder to choose the unitaries that will be able to sort of measure it. It turns out that, yeah, in the case of, say, QWC, it's the kind of the worst in terms of the post-selection approach, because it really doesn't allow you to measure any of the symmetries that other techniques would allow you to measure, because simply it's sort of flips things, and Adamar and Space kind of break most of the operators here, symmetries, because the two symmetries that kind of could be measured with the fully commuting case is this product of all Z's. And that is exactly -1 into the power of number of electrons. with maybe some prefactor, and this could be generally measured with every Pauli that comes from the Hamiltonian, simply because every Pauli that comes from Hamiltonian contains only even number of x and y xy operators in it. And so if you have a full set of z's, then you always will have an even number of differences. Okay, so this parity measurement could be done always and post-select based on the parity measurements. Okay, so now what can we do in the situation where these symmetries are sort of there, but we cannot measure them, right? So there is this different protocol. It's a symmetry verification by post-processing. Okay, so this post-processing is working based on the group property of symmetry operator. Group property. So to remind you, the group is a collection of objects where you can define some multiplication. They call it multiplication, but what this operation is just a binary operation that allows you to get from two elements some third element from the set, right? And then this operation is associative. A group needs to have identity so that any element could be multiplied by identity from left to right and gives you back the same element. And then every element has the inverse element, so that so then again from any side g minus 1 equals to identity, right? And so you need to have associativity, identity, and inversion. So those are three necessary conditions beyond the fact that if you do any two elements, you should get the element from the set, right? So you cannot get out of the set by doing this product. And so if you have some operator that commutes with Hamiltonian S1, then if you have another operator that commutes with Hamiltonian S2, they may not commute with each other, but S1, S2, if you just make a product, clearly will commute with Hamiltonian as well. Right, so you just do commutation one after another, and so this will follow. So the property, if you have some operators that simple and commute with Hamiltonian, use them as symmetry operators, and clearly you could just use operator multiplication to create well, more operators if you want. So that's why symmetries very frequently, yes, in all the cases, they form a group. The only question is whether group is finite or infinite, right? So the simple version, like what you're probably familiar with, the point groups, and one simple aspect, like I guess one simple version of the point group would be just like my favorite simple example would be kind of in case of harmonic oscillator, where you have a parity, you could switch parity operation. It just switches x to minus x, right? And then that operation done twice, it's identity, right? So parity squared is identity, and then you could say that identity and parity, they form a group. And with two elements, right? And no other element is actually appearing. So why all this kind of theory is useful here is because on top of the abstract group theory, there is a theory of a group representation. And by representation, I mean we create a map between group elements and usually operators represented as matrices. You could think of them as like that we have some operators that could potentially act in multiple spaces, and depending on what space we select, there will be matrices depending on, of course, the space, right? So the representation theory talks about group properties based on the properties of these matrices that are transformation in linear spaces, right? And this is one of the most useful for quantum mechanics branches of the group theory, representation theory. And I guess the motivation for studying that is that there are a few very valuable kind of consequences. One that I will be using here is simply that you can construct the projectors onto irreducible, so-called irreducible representations. We will construct projectors onto irreducible representations, the wraps of symmetry groups. All right, so what are a quick reminder, what are the irreps and why are they important? Irreps essentially is the generalization of eigen subspaces for the set of operators that don't commute. All right. So if you have operator A and B and they don't commute, which is frequently the case for some group elements, right? So if you want the example, let's say C3V, the point group symmetry, right? So then there are multiple group elements, planes, and the C3 axis, and so some of them don't commute. And so the operators that correspond to these group elements, because non-commutativity of GI, GJ is not the same as GJ, GI, translates into non-commutativity of matrix multiplications corresponding to the group elements, right? So J, Mi. What I guess skipped to mention is that the whole point of the whole notion of the representation theory, the most important notion of representation theory is so-called homomorphism. But in this case, in many cases, we're actually going to be using isomorphisms, which is a somewhat simpler version. And the idea is that why this isomorphisms will be very useful for us is that these abstract objects, and they are indeed very abstract. You could sort of fill with this with many objects, these G's and numbers, operators, you name it, right? And this is a very concrete object, matrices, and with matrices we could do linear algebra very efficiently, especially on the classical computers. So, one great thing about isomorphism that representation theory allows us to do is that operations between these abstract objects, this abstract multiplication, will translate into the very concrete linear algebra matrix multiplication. So essentially what this means is in order to get the result of GI times GJ, we know that it's some sort of GK because they form a group, right? But what we can get the GK essentially from doing the matrix multiplication of mi with mj, getting the matrix mk, and then seeing what, according to this map, what group element can we build for the like corresponding to this matrix, right? So the fact that we can do algebra in the matrices and then go back to the group, that is very valuable, because if you want to do the group algebra, it's well, it's somewhat tedious, and sort of groups could be large, and yeah, it's generally more convenient to work in linear algebra spaces where the algebra could be very efficiently done. Okay, so that's the kind of the reason. But going back to the operators, let's say if they don't commute, then well, then what we can do is we cannot diagonalize them. Essentially, we cannot find the basis where both A and B matrices will be diagonal, but we can find the matrix, basis where these both A and B will be block diagonal, meaning that there will be some subspaces where if A acts on the element of the subspace, it may not, like A acting on the element of the subspace, it may not be necessarily lambda phi 1, but instead it will be, say, something phi 1 equals to phi 2, and then A on phi 2 gives you back phi 1, right? So it's essentially subspace where when you act with one of these operators, you only obtain the states from the same subspace, right? And that you can do. This is if you can, of course, you will try to reduce the subspaces to make representation of the operators as small as possible, the subspaces as small as possible, but there is a limit which group theory and representation of group theory defines. There are limits that you cannot pass, and essentially this will be irreducible representations, right? And interestingly, the group theory, if the elements that don't commute form a group, the group theory allows you to build the projectors onto these irreducible representations. Essentially, it allows you to build projectors in the subspaces where group elements act in the simplest possible way, and it cannot be simpler, right? Because we know the operator is in this, the simplest representation of the operator is a diagonal matrix. And for that, you need the eigenbasis, right? If you have multiple operators, the simplest representation is block diagonal, and it cannot be simpler if they form a group. And the group theory sort of shows how to build the subspaces that are reducible. Okay, let's see. This. All right, so this is just a long way to say that we can now build these projectors using the group theory, and this, for those who didn't ever seen this, yeah, maybe a good motivation to study the group theory representation in particular, because it allows you to build these projectors. And the formula is very simple, but it's very useful. So let me write down the these irreducible representations. They are essentially named, usually use gamma for the name for the different kind of indices of the irreducible representation, and projector is constructed like this. It's a dimension of irreducible representation, number of elements in the group, sum over let's say symmetry elements inside the group. We have symmetry element I, and then with the coefficients that are called characters of irreducible representations. And so these characters are just traces of operators, right? So there are ways to, there are character tables where for standard groups there are kind of built values of these characters. And the important thing is that if you want to project onto the reducible representation, all you need is just to include the sum over group. Okay. And how is this helpful? Let's imagine if we study expectation value of the Hamiltonian, and there is a chance that our function will be corrupted with the error. Then if we want to remove the errors that correspond to breaking the symmetry of the function, what we can do, we can go from this corrupted expectation value to the projected one. So we have projector onto irreducible representation, H projector psi tilde divided by psi tilde projector squared tilde. Our projectors are Hermitian, that's why I don't put the dagger here. Also, they are square of the projector is projector again. Quite important, right? So in order to correct the expectation value with a corrupted wave function, we need to calculate two expectation values. And well, some simplifications here could be done. First of all, this projector, because it has only symmetry elements, right? It will commute with Hamiltonian, and then reuniting with another projector, you will get the same cancellation of square. So what we really need to calculate is just the H and then projector. This. This, right? And so this will require, if you think about it, it will require H times S from the group, right? So instead of measuring H, we need to measure elements like this. And then here also elements like group elements. Okay. And so that is post-processing because technically we're allowing the errors to occur and we just projecting them out, right? By combining everything in these expressions. So it's yeah, more tedious, laborious process, but depending on the group, of course. So the group that I already mentioned, my favorite, because it's very simple to illustrate. So if we use a group that contains only identity and parity as two elements, and that is exactly the same group as, say, parity in the case of number of electrons, right? Then this formula becomes simply, in these situations, the 1/2 sum of identity plus minus parity. No sum needed actually, right? Plus corresponds to symmetric irreducible representation, and minus corresponds to antisymmetric, right? Because it corresponds essentially, you could think of it as if you have a function of x, and this function is just a general function, you could always, using this projector, build symmetric and antisymmetric versions of these functions. So symmetric one will be just the sum of x plus f with minus x divided by 2, and the antisymmetric will be with the corresponding minus sign. Right. So this is a simple use of this formula. Now, if we want to use it in this context, then we have a Hamiltonian and with identity plus Hamiltonian multiplied by -1 in terms of number of electrons, right? Divided by 2. That's the kind of a modification of the Hamiltonian in the numerator, and in the denominator is just really 1 plus -1 number of electrons divided by 2. But here plus minus depending on which sector you want, even or odd. Right, so that will allow you to do post-processing, removing the errors that changes the parity. Any questions?
But I can only do this in FC.
You could do it in NFC. You could do it also in QWC, right? So let's, as long as the Hamiltonian commutes with symmetries, you don't need to worry anymore about the function. Even if you construct a function that is breaking symmetry, that's fine, because this construction will take only the part that is symmetrically correct. You could also think, like in old days when people used Hartree-Fock restricted and unrestricted version. Unrestricted broke spin. Then there's a loaded projection. So this is exactly what's happening here. Essentially, if it's a broken spin, you could correct the spin, and this will become like a multi-reference state, because this formula will apply the symmetries and multiply with some coefficients, right? So, and will create multi-determinant expansion.
So how would I do it in QVC?
QWC? Well, you take the symmetries of the Hamiltonian. Let's say if you want to use so the easiest would be the parity, right?
Mm-hmm.
So what you need to do is you construct a numerator operator, which is like this, and this being the product of these, right? So this probably is a better representation. Products of these. H. Oh, okay. So H, imagine, is a linear combination of Pauli products, and then you, on top of that, multiply it with H needs to be multiplied 1 plus product of these divided by 2, right? So that will technically almost like a double the product, but still it's a linear combination of Cn and then Pn, then 1 identity plus product of these. So this is just effectively a single extra Pauli, right? And then what you do is you do QWC breakdown of this operator, right? So you got yourself an operator. It's a little bit more complicated than the original one. You do the QWC on that. You do the measurements. You get the numerator. And then what you do next is you need also denominator. So for denominator, you just measure, well, identity you don't need to measure, product of these, right? So that is measurable in one go, right? So it's actually already probably present in H, because H is a constant. Yeah.
But it's for free.
It's almost, yeah, for free. Well, it's for free only if your PNs multiplied by product of these will already be in the H, which I'm not sure is the case. Right? So there will be some extra Paulis.
Yeah, but if you think, I mean, on noise device, that might, if you can post-select suddenly much more.
It's not post-selection, it's more post-processing, because you're not removing any result. You allowing the noise to corrupt your wave function, but your projector will take care of that.
Yeah,
that extra noise. Yeah. So, and then why this is still a bit limited? Again, going back to this formula, which is useful, but it has a limited, value, because if you go to the number of electrons, then this formula becomes, projector essentially becomes too complicated, because the number of element in the case of number of electrons, it's bigger number. So there is essentially number of electrons sort of is really forming the continuous group. It's a just generator. It's I number of electrons phi. This as a group, this is what forms group. And then you need to integrate instead of summing. But if you doing some approximation, a subgroup of that group will essentially boil down to Lövdin projection on the number of electron states. But because the number of electrons generally is large, so you you probably will not use the whole polynomial of the Löwdin. We discussed that Löwdin would be like this, divided by n j minus n I. So where, let's say, I is the right one and j is the one that you want to project. So you may want to think like the following way. So in order to simplify the projector, you could leave only few terms in this product, because the thinking is the following. So let's say it's very frequent maybe that like there is a flip of the one qubit, and that makes the, say, number of electrons from 10 to 9 or 11. And so 9 and 11 are most frequent errors, so you want to remove them, right? And so the others, they are less frequent and you don't put them, and so the projector becomes somewhat simpler, right? So in that sense, the operator is always going to get more complicated, but at least you may be able to make some kind of approximate projection that only removes certain number. But in general, if you want to be very accurate, no approximations, the projector on number of electrons is complicated operator, right? So that's the issue with this. The same with S square, the same, yes, Z is the same. So it's only very simple operators could be used in this type of formulas, okay? Because of the algebra. Okay, so let's make a quick break and reconvene after.
Is it studied in a more systematic way? Like, I don't know, for some systems and Hamiltonians, how much it scales and measurements if you do that?
Right, so that's what actually we are trying to finish with one of the graduate students in my group.
Okay, good.
Because again, different grouping techniques, they were analyzed mostly in ideal case scenario, right?
Yeah.
And what we wanted to understand is that, okay, all these symmetry related tricks, because they are not always compatible with every grouping. So maybe the more sophisticated groupings would still allow you to, because they allow you to do a lot of error mitigation based on symmetries. Maybe it's not going to be that bad. Maybe we could revive them or make their reputation better, because they could be error mitigated more efficiently. So that's what.
But I mean, even that for QVW, you could try that. That doesn't sound like difficult.
Yeah.
It's just like a few more measurements.
Right. It's true.
Unless, of course, it's not. I don't know. Multiplication by z's, maybe it's fine. I mean,
it should be fine. I think the results it's still kind of ongoing sort of study. Hopefully will be available soon.
oh, that's nice. That's very cool. something what oh, but the annotation potential is fine. I mean, they were done 2 minutes after I submitted the calculations. They take no time. The energy calculation takes 2 seconds. After that. Yep. Oh yeah.
Okay. Learn. So I guess in the second part, what I want to finish with these 2 aspects that were left before, and essentially how do we construct the unitaries that diagonalize or essentially bring the fragments that one would like to measure to the form that contains only z's, right? So we need that. And the 2 big, I guess, type of fragments is the fully commuting and the fermionic fragments that we talked about, but I didn't go into the construction of unitary, just assured you that there's unitaries could be constructed. And it turns out that, well, first of all, for the full commuting case, it's non-trivial situation, and it has a very nice geometrical sort of construction in it. Also, the same geometrical construction or algebraic construction is used in so-called qubit tapering technique. I guess both could be related to the so-called stabilizer formalism in quantum computing that chemists, yeah, it's not the first thing that they study, but it's somewhat the quantum computing science, I guess, literature. And yeah, it would be nice to maybe review it somewhat, or at least give you some kind of a sense of direction, because when I first time tried to read this paper by Braui and coworkers from IBM, as you could see, it was put on archive January 2017, but it's still unpublished. Actually, it has not like in any normal journal, the peer-reviewed journal. It has more than 100 citations, because especially in the early days, people if you're not familiar, what qubit tapering is like essentially being able to, if you do the Jordan-Wigner and end up with 10 qubits for the 10 spin orbits, then with qubit tapering you could definitely remove at least 2 extra qubits. So in the early days when the qubits were precious, this sort of technique was very, very useful. But it turns out it's kind of a more general technique. It could be the same ideas could be used to turn the fully commuted groups into the measurable fragments. And it's just nice to kind of, I guess, discuss these formalisms, because they are, in both cases, what the key ingredient will be is a map between the operators and linear spaces. Okay, so the operators, after all, is something that also form linear spaces, but you could think of it as it's like a very high dimensional linear spaces in general. And if you can figure out the way to represent operators as in a finite, very like not exponentially large, but with a number of qubits polynomial or linear, maybe linear spaces, then the matrix algebra is very efficient in this like small dimensional subspaces. And so if you could map operators to these matrices of n by n, where n is the number of qubits, then lots of things will be easy to do. And that's what is happening here. Okay, so first let's talk about fully commuting and qubit tapering situation. So let me remind you, we start with, I skipped the subscript here, but and this is not the entire Hamiltonian, this is just a fragment, right? This is a fragment which contains a linear combination of Paulis, and all the Paulis inside the fragment, they commute with each other. Okay, so that's the setup. Now the question is, how do I construct the unitary that will transform this Hamiltonian into Hamiltonian that contains only qubit-wise commuting terms, right? So then I can easily measure that, because for the qubit-wise commuting, all I need is to turn x and y's into the z's, and we know how to do it, qubit after qubit, right? So all we need then is to get to this, and we know how to solve the problem. All right, so how is this done on a kind of high level? So on a high level, it turns out that it's possible to show that there is a set, there are two sets that we can build, and in both sets of operators, these are operators, in both sets we have n, where n is the number of qubits, operators, and they have very nice commutativity properties. So the T set first is the set of taus, and those taus are Pauli, you could think of them as Pauli products, which commute among themselves and commuting Pauli products, and they commute also with the Pauli products that were in the Hamiltonian. All right. Of course, in the Hamiltonian, generally here we could have very many Pauli products, and here we have only n. Okay, but then what this taus will be used for is actually representing every Pauli in the Hamiltonian, right? So the taus, product of taus, could be used to present any Paulis, and up to the phase factor of plus minus y, right? I, right? And then there's a Q set, which has the following properties. And first of all, it's a single qubit Paulis, right? So this could be sigma x, y, or z, and so on. So up to n. And the conditions for them is that they anti-commute with taus, so but only corresponding sigmas. So sigma I anti-commutes with tau, but sigma j, if j and I are not the same, then they commute. Okay, and then of course single qubit Paulis on the different qubits, they also commute, right? So now so far I just assumed that these such sets exist. Okay. All right. So what's the use in such sets? It turns out that if I have such sets, first of all, I can present every Pauli as a word that taus are letters, right? And then I know, I'll write in a moment, how to construct unitary so that every tau will be turned into sigma. Okay. And if that will be accomplished, then simply, if I can do that, then this same unitary will do the job here. Why is this the case? Because you could think, okay, so let's just knowing this, let's see how this is true. So this is unitary applied to Cn Pn. Right, so okay, so this is linear, Cn unitary, Pn unitary. Now every Pn can be written as a product of taus, and then I can just write unitaries kind of acting on the taus with some prefactors, right? And then this will be prefactor product of sigmas. At sigmas are different qubits on the different qubits, right? And they all kind of commute either with themselves or with each other. And what this will be eventually is a sum of Cn's up to some prefactors that are related to n, I guess here, and then product of sigmas. So this is qubit-wise commuting, Hamiltonian, because we have a set of, you could think of this sigmas as being all z's, let's say, or ox or y's, whichever choice you want. Okay. Now, okay, so now how do I construct this use? Knowing taus and sigmas. And this is so far as a purely algebraic exercise because I didn't explain what taus, like I didn't really go much into the how I'm gonna get the taus and sigmas. If they have these algebraic properties, they will do the job essentially, right? And more than that, the unitaries could be written as products of the following products. It's the product of tau I plus sigma I divided by square root of 2. Okay, this very simple form. Now, this should remind you yesterday's lecture, tau and sigmas, they anti-commute. When you sum anti-commuting operators with normalized coefficients, they are unitary. Yeah, they are back to the essentially being unitary. We've seen that yesterday. They form sort of a Clifford algebra, and yeah, so that was shown yesterday. But let's see today. Effectively, you can call each element as a VI, right? And U is essentially a product of these VIs. Now, if we apply U to tau I, then it's easy to show that well, essentially all you need is VI tau I VI dagger, because Vj will commute with tau I, and so so for particular I, only Vi will do the modification, and Vj's, because they will correspond to the here J's, they will commute with taus because tau I and sigma j commute and all taus commute. So therefore, Vj will commute with tau I. All right, but now let's see what this is. This is a little bit of algebra. So it's actually tau I q. Okay, so let me write it carefully. So it's tau I plus sigma I. Then you have tau I, and then another tau I plus sigma I, right? So that's what it is. And turns out, you could write it opening the brackets, tau I cube plus tau I square plus sigma I tau I square from this side plus sigma I tau I sigma I divided by 2. Okay, and then what we can do, first of all, tau I square, those are identities because they are Pauli products, so squares are identities. So the same with just the tau I for the cube, right? So only a first power is left. Then sigma I, since it's 2 sigma i's here, plus here we have sigma I, tau, sigma I. So we could move sigma I through tau, and that's because sigma and taus, they anti-commute. So that will change the sign and sigmas will disappear. So we will have tau I, yes, with a minus sign, right? And they cancel with this tau I, and we will only left with 2 sigma i's, but they will have a divide by 2 coefficient. So this is sigma, right, as promised. right? So as promised with this condition, right here, that unitaries acting on tau I give you single qubit Pauli operator. Okay, so I don't know how did they come up with this. This is sort of the idea of essentially moving from the Paulis to individual qubit operators that are commuting because they are on a different qubits. Okay. Now, how do we prove? How do we? Well, first of all, now if someone is giving you Hamiltonian, you need to be able to form the T and Q sets, and then you're done, right? So, but you need to build these sets. That is sort of non-trivial problem. And how do we build these T and Q sets? That's where what is helpful is now this mapping between the Pauli products and vectors in linear space. Okay, so turns out the Pauli products could be mapped to vectors, and for notational simplicity, I will separate essentially the kind of the components of these vectors. So the Paulis of the n qubit space, they could be mapped to vectors. This is a vector, also P, but with a bar on top, right? And the simple thing here, actually, this encoding is, you maybe even seen it in other places. So this vector will contain essentially n points here and n entries here. So overall, it's a 2n dimensional space. Right? So we don't really we didn't grow too much. And here there will be numbers, zeros and ones. Here will be numbers, zeros and ones. So what these numbers mean is the following. So let's say Pauli for ith position here, it will have only 4 choices. So it's either identity on the ith position, then X, Y, or Z, right? And so then on the ith position here, and the n plus I formally position here, what we do is we encode these 4 possibilities. So the identity will correspond to have a 0 on the I and 0 on the n plus I position in the vector. Then xi will correspond to having 1 on the, this is essentially the X register, and this is one is Z register, you could think. So then zeros everywhere else, psi. Then Y, we can obtain Y by multiplying X and Z. And so then what this corresponds to is having 1I here and 1 on n plus I position. Right, and for the Z, we'll have encoding where it's 0 on I and 1 on n plus I. Right. So this is the way to construct vector based on what do we have on the ith position of the operator. Okay. Now we can take 2 operators, P1 and P2, and see, and they will be either commuting or not, or anti-commuting. P1, P2, anti-commuting. Those are the 2 choices. And so this vector space that we organized, it's going to be, well, a linear space. So we have vectors. Now, the other component of any linear space is field, right? So field meaning that we can multiply vectors by numbers. And these numbers will be only 0 and 1. So it's a binary field called Galois field characteristic 2, Z2 sometimes, but essentially it's a binary field. Why is it field? Because you can essentially do everything you can do with normal numbers. So you have addition, multiplication, and the only thing is that there are conditions like 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. It's modulus 2 essentially, and then 1 times 1 is 1, 0 times 1 is 0. Yeah, so those are the operations of the field essentially that you need to be aware of. 0 times 0 is 0. But okay, so this these two operations that we have for the commutator and anti-commutator, they correspond, turns out, to the interesting inner product between the vectors. So if P1 vector inner product with P2 vector is 0, then that corresponds to the commutativity of the two operators. And anti-commutativity of two operators will correspond to the situation where P1, P2 equals to 1. Okay. Now this is the inner product organized in this space, but it's organized in an interesting way. So the usual inner products, that's like the way we think about in the normal linear algebra, it's just the xi, maybe with the conjugation, yi, sum over I. So this is one way, and then you also may have seen in the, let's say, if we add some metrics, then this could be some sort of, in reality, more like some matrix Y, some quadratic form, which is positive definite, and it's then it's xi, mij, yj, sum over ij. But in this case, none of this is going to be the case. Well, actually, this part is relevant because the space we organize, just depending on how we choose this matrix, it can be called, there is some class of linear spaces which are called symplectic. So symplectic, and in symplectic spaces, they are defined by the fact that some part of this matrix is, or like eigenvalues of this matrix are negative. Okay, so usual metrics they are all positive, but in symplectic spaces they are allowed to be negative. And the way we introduce this inner product is that one can say it's P1, P2 is written as a P1, and then the normal, in the normal sense, in the sense of the coordinate-wise multiplication. But then there is the J matrix here, P2. And what J matrix, what it does, it has the following structure. J matrix, it's 2n by 2n. And it has a very simple structure. So it has ones, so essentially, identity in the block this block n by n, and then 0, 0 on diagonal, and then again here identities. So essentially identity matrix in the all diagonal blocks n by n, and zeros in the diagonal. Okay, so this is a J, and a simple way to think about this inner product, what it does, if you write P1 as a, let's say, sigma 1, sigma, okay, sorry. So if you write P1 in terms of, there is a line corresponding to, let's say, X, and the line corresponding to the Z entries. And then this is P1. And then for the P2, it's X1, Z1, X2 line, and Z2 line. Right. So what J matrix does, it makes you to multiply X by Z's and X2 by Z1. Right. So, and then add this up. Right. So you do the normal inner product term by term and sum them modulus 2, like this and like that, and then add up everything. And don't forget that 1 plus 1 is 0. Right. And so on. So essentially, that's the construction. Now you have a space where previously commutativity of operators correspond now to the inner orthogonality. Okay, and anti-commutativity to having the inner product equals to 1. Interestingly, in this case, this space, like in a normal space, number of dimensions. The number of dimensions here is 2n formally. Normally number of dimensions is equal to the number of orthogonal vectors, linearly independent orthogonal vectors. But here, because operator commutes with itself, what this means is the inner product of operator with itself, inner product of P1 with P1 will be 0. So that corresponds to the vectors which are self-orthogonal. Okay, that's a kind of interesting feature. So now working in this space allows you to construct the taus and sigmas, and it's in this paper we discuss in appendix the details of the construction, but it boils down essentially to, I think, 2 operations that you are familiar with in the linear space. What are these operations? So technically, you can construct now. Your original Hamiltonian was a linear combination of Paulis, and those Pauli products correspond to the vectors in the space they which commute with each other, so they're mutually orthogonal. Okay, and then the taus, they are extra vectors that will also be orthogonal to this system. Okay, so technically, if you write all these vectors like a P1 and then P2 and so on as a matrix, the n, no, large n, but let's say small n, right? And then the tau vectors will be some, okay, so you could think of them as a vector like this. Where it's separated the x component from the z component, right? And the taus must essentially, when I multiply them, do this inner product, I should get zeros, right? So what this should remind you is the process in the normal linear algebra. So here, the algebra could be very close to normal, with just minding that operations, when you do the inner products, they need to be done in with this J metric, right? But other than that, it's all the same. You could, since it's a linear space, you can analyze linear dependency. You can analyze the orthogonality sort of through this inner product. And what the procedure that builds the taus effectively is the procedure that we are familiar in this problem as building the kernel of a matrix, right? So kernel means that find me X that, or the basis of subspace, which will always generate zero sort of vector, right? So the taus, they must be sort of commuting with all these operators. And so in the linear space language, that means they must be orthogonal, right? So that's it. You construct this matrix in the 0-1 space, and then you do Gauss elimination. And then for Gauss elimination process, you can find the kernel of the subspace, and that kernel you can construct the like a basis of that kernel subspace. Those will be taus, and then more than that, you could decompose all this piece through that like essentially basis. That's step number one. We could build taus like that, and then step number two is how do we build sigmas? So sigmas are built using a second, or one more procedure that we're familiar with linear algebra is orthogonalization. Because if we have taus, let's say tau 1, then sigma 1 must be anti-commuting with tau 1. And that is not that hard to get, because if you have a bunch of, essentially, let's say tau 1 have x1, and then other qubits. So then if you want something that is only a single qubit operator and anti-commute with this operator, all you need is just to take y1 or z1. Because you know the tau has x1 to get anti-commuting single operator, you could use this too. All right. Okay, so that's easy. But now there's a second condition that the tau 2 and other taus up to tau n. So these guys, they need to commute with whatever we made the choice for this guy. And how do we make sure that this will commute with sigmas? Sigma 1 that we've chosen. And on the linear space language, we need to make sure that these guys are orthogonal to sigma. And that's Gram-Schmidt orthogonalization. So these guys are vectors, and this is a vector. So we just need to make sure that tau 2 is orthogonal to sigma 1 in that sense. And then it's not only tau 2, but all the k that is 2 to n, right? Of course, that may require us to modify the whatever taus we got. That's okay, because it's nice that first of all the vectors are self-orthogonal, and making a linear combination of vectors doesn't break the orthogonality or commutativity, because I guess from this picture, one can see that if you make a product of operators, P1, P2, that is up to, again, a phase factor, that corresponds to essentially making a linear combination of two vectors, right? So the product of operators maps to just a linear combination of operators, and if two operators commute, then making products of commuting operators doesn't break commutativity. So the same way, if you make a linear combination of orthogonal vectors, you don't break orthogonality. And so then the last, I guess, expression here is that if you want to modify the tau 2 in order to be orthogonal to sigma 1, so you take whatever tau 2 is, and following Gram-Schmidt orthogonalization, you add the sigma 1, tau 1, sort of the procedures like this. And that way you can make sure that even if the original taus were not orthogonal to sigma 1, by doing this, they will be orthogonal, because it's like essentially doing the Gram-Schmidt optimization. That way we could obtain tau1 and sigma1s, or the whole set of taus and the whole set of sigmas. Okay. Any questions? Yeah.
I hope I don't grossly simplify.
Yeah.
But isn't that maybe the same or very similar to creating a stabilizer matrix of a set of Pauli strings and then trying with operation that switches rows, try to get a diagonal, an identity matrix in the Z part.
Right.
That's
Yeah.
the
So
thing.
that's the same thing. Yes.
So it's just then trying to find the operations that switch rows or add rows to represent gate structure for our circuit.
Right. Yeah.
It's
So
the same thing.
it's the same thing. The only thing is that I was not relying on the stabilizer formalism, right?
Yeah,
Because
yeah.
then you need to learn what stabilizer formalism is,
Yes.
right? And then to express in that language. So here I relied on the essentially isomorphism between built between the Pauli operators and binary vectors, right? So then, and that isomorphism is probably what stabilizer formalism is using, right? So in that sense, it's all connected. It's just the question, what is the base? So also all the linear algebra operations could be used and in order to essentially get this 1000 sigmas. Okay. Now the last thing about this formalism, I guess, is related to qubit tapering, right? So qubit tapering is slightly different because in a qubit tapering case, we have a Hamiltonian that is not necessarily contains all the commuting Paulis. It's a general Hamiltonian, right? So we have a H that contains just a linear combination of Paulis, and what we do, Pn and Pn prime, not necessarily zero, not all, not for all terms, not for all and then primes, right? But we have, suggestively, we could say the tau operator, one, say that commutes with H. And this is this kind of, it commutes with H in a way that it commutes with every Pauli in a, commutes with every Pauli in H. Right, so for any n. So that's the condition that we have for qubit tapering. And of course, it could be one such Pauli product outside of the H or inside the H, doesn't really matter, or multiple. But with one, it's let's say we have one. What can we do with this information, right? So now you could actually, with using the previous sort of stuff, we know already that there is a Clifford transformation. We called it V before, V1, that is tau1 plus sigma1 divided by square root of 2. Right, and with this Clifford transformation, what you can do, you could transform tau1 into sigma1. Right, so essentially, whatever Pauli product you found that commutes with H, you could always transform it into the single Pauli operator, like let's say Z1. You could always do that, or any other number, doesn't matter. And that is, it's very powerful, turns out to be a very powerful kind of fact, because what this means is, okay, the tau1 commuted with H, then that means that sigma1 will commute with the transformed H, because the unitary transformations that they don't change the commutativity, right? So from this, we could just simply say that sigma1 will commute with the transformed H. Right? So this is 0. And the fact that your Hamiltonian commutes with, let's say, Z1 or sigma1 in general, that restricts the form of this transformed Hamiltonian significantly, because I'll show very, very simply in a moment that this, let's say, transformed H tilde, if sigma1 is Z1, so H tilde can only be something of that, let's say, acts on the either second or nth qubit, like some operator like this, multiplied by identity on one, plus something else in 2 to the n, multiplied by Z1. Well, where I assume sigma1 is Z1, right? So this is the only form of H transformed that is possible. And there is no way it can have Y1 times something, H tilde, and or X1 H bar, let's say. Right, so these terms are not allowed. And it's very simple to convince yourself why, because if you have a term like this, then the commutator with Z1 for the term like this will, well, commutator of Y1 with Z1 will give you X1, commutator of Z1 with X1 will give you Y1. So there will be no way to cancel something of this kind by something of this kind, because they will produce different terms, right? So that's why there is no way you could have terms like this in order to have a commutator equal to 0. So the only transformed Hamiltonian form you can have is like this. But that means now in this frame, the eigenstate of the Hamiltonian like this, eigenstate of H tilde, if it's an eigenstate, it must have a form where you must select for the first qubit, it's either 0, something on the 2n, or it's 1 on first and something on 2n. So these are the only possibilities. You cannot mix two, because if you mix two, the Z1 will make a +1 for one and -1 for another. So the mixture will never be an eigenstate of this form, right? So identity is fine with mixture, but the Z1 will definitely recognize that, okay, that's not an eigenstate. So the only way to build eigenstates is like this or like that, right? So what this means really is in the more like a symmetry related language, we have a symmetry of the transformed Hamiltonian that is that has an eigenvalues of ±1, the Z1 symmetry, right? And that means in that new basis, the matrix of the Hamiltonian, which is 2n by 2n space, it has two blocks. One corresponds to -1 and another corresponds to +1. These are like a blocks of the transformed Hamiltonian. Because and there's no kind of coupling between them. Okay.
Some array goes directly on the camera.
Okay. All right. Yeah. So then we could in our transformed Hamiltonian, we simply can substitute Z1 by +1 or -1. Depending on that, we are working either with this block or with that block, right? So So then the tapered Hamiltonian, the H tilde after tapering, will be either H 2n with at plus H 2n with a prime or with minus, right? So essentially you will end up with a Hamiltonian that contains only n minus 1 qubits, right? So that's the tapering mechanism. Okay.
I don't fully understand it. How do you find that symmetry?
How do you find that symmetry?
So
So-
if you have the symmetry, I understand why you can
Mhm.
do that, but how
Right.
do you?
Okay. So for finding the finding the symmetry, you need to find the tau that commutes with H, right? And that's again in the geometric language is finding the vector from the kernel, right? So you write H as a kind of elements of like all the p's, and you find the vector that is orthogonal to all of them, right? So that gives you tau. As long as you found a symmetry that is a single Pauli product, then you're in the game, because then there is a known transformation, Clifford transformation, how to turn this tau one into sigma one, and that just results in the symmetry that is only a single qubit, right? And that is very powerful because then there is no way you can. It simplifies the structure very much.
Didn't you say in the beginning you can maximum remove 2?
Right.
What does that
So
relate to?
okay. So what is related to? It's to -1 into the number of electrons alpha and -1 in terms of and electrons beta. So those are Pauli products that let's say P alpha and P beta that correspond to, well, they will commute with Hamiltonian.
So is that only working in specific mapping?
I think it yeah, it will work for any mapping because this I think for Jordan Wigner and Pauli Kitaev, it will be for some mappings this becomes very simple. Meaning like for Pauli Kitaev mapping, it could be as simple as just having a z term for the this instead of z1, this being z number of electrons, sort of alpha, and then depending on the order, this could be a little bit more complicated for beta. But let's say for -1 in power of NE, that is another Pauli. In the Jordan Wigner, I think it's a product of Paulis, Z Paulis, but in the case of Pauli Kitaev, it's just one Z that corresponds to the, I think, the number of
I
electrons.
was just wondering, because doesn't it kind of relate to parity mapping, where you kind of have this removal of 2 qubits just by the way that
Yeah.
So
Right. So, well,
I wonder, can you
But wait,
separate on
parity-
parity mapping on top?
parity doesn't remove qubits. It just reformulates everything that Jordan Wigner has.
Yes, but with 2 qubits less.
No, it's only the removal is based on this mechanism probably. I'm not saying that removal is impossible, but the removal is possible in Jordan Wigner. Removal is possible in Pauli-Kitaev. In every mapping, essentially removal is possible because there is an encoding of the symmetry as a Pauli product. That's the origin of the removal, right? So if we had more Paulis that commute with the entire Hamiltonian, then we could remove more, right? So, and technically this problem where we have full, all the Paulis are commuting with each other, technically in this case, we taper all the qubits that are present because we can find the taus, n of them, that will commute with all the stuff. But in the normal Hamiltonian, we can definitely find only 2 Paulis that commute. Now there is a work also on top of this. There is a work where people use point group symmetries, because if you think about what's going on here, technically what's going on, this is the key of the tapering, right? So that you need somehow to find the frame in which the symmetry that of the Hamiltonian will be just Z1, let's say, right? And if you found the Pauli product that commutes with Hamiltonian, then Clifford transformation will go from the Pauli product to Z1 easily. But what if the symmetry is not a Pauli product? What if the symmetry is like related to the like a C2 axis? It still can be done. It's just the unitaries that will make the symmetry look like Z1. They will require non-Clifford transformations. So the point here is that symmetry is powerful because it has the subspace, the irreducible representations, which are only plus and minus one. And so going into these irreducible representations make the Hamiltonian look simple. And then you could just essentially substitute operators by numbers and taper the qubits. Okay. So in the original paper of Bravi, one thing I think that is called incorrectly is they call the symmetries as Z2 symmetries. And what actually is done is using the fact that the symmetry is symmetry equivalent to a Pauli. Why Z2 is more general is because Z2 is any operator that if you square its identity, but Paulis are more specific version of that because yes, indeed, any Pauli squared is identity, but also Paulis are traceless. So the number of plus ones and minus ones in the spectrum of Paulis is the same. That is not required to have p squared equals to identity, right? So in that sense, in order for the symmetry to be equivalent to Z1, you need the number of plus ones and minus ones in the spectrum of the symmetry operator to be the same. Then you could taper the qubit. But if it's not the same, then it's a different symmetry and you won't arrive to the same expression by doing some unitary transformations. Okay. Yeah.
I'm not entirely sure, but like the P, like the projections, they are orthogonal to each other as well. The P1 to P2 to up to Pn, or are they?
What do you mean by like in order to talk about orthogonality?
Yeah.
We need to define the inner product, right? So there are multiple ways to do it. Are you referring to the inner product I defined there?
Yes.
Okay.
Yes.
So inner product I defined there essentially takes an operator, creates the vector, and defines inner product on the binary vectors, right? And zero of orthogonality essentially between the two vectors correspond in the operator sense to commutator being equal to zero, right? So that isomorphism of operator space to the linear symplectic space makes a connection between orthogonality of vectors in the symplectic space with the commutativity of operators in the space of operators, right?
But we are in this symplectic space to find actually tau, right? Or
yes, that's right. So symplectic space, the whole point of going to symplectic space is because in linear algebra, there are lots of operations like finding the Gaussian elimination process, finding the kernel of linear, linear transformation, right? So those are very easy to do if you if you are looking for orthogonal subspaces, they are easy to find using this linear algebra procedures.
right. My question is like, I mean, to find the tau, isn't this then already overcomplete if you want to find?
But you see, yes. So in a normal sense,
Yeah.
it sounds like it's overcomplete.
Yeah.
But in the sense of the symplectic space, let's say you have you have a self-orthogonal vectors. All the vectors are self-orthogonal, right? So in that sense, orthogonality and dimensionality, those are two different things. So like in the normal sense, we're thinking, okay, the number of orthogonal vectors cannot be larger than the number of dimensions. But there that's not the case anymore because of the binary field also.
Yeah.
Yeah, so that's why I didn't want to drag you through the procedure of the Gaussian elimination, because
Right,
there
right.
it's a it's a
Okay, thanks.
bit counterintuitive. But it is based on that essentially. Right? All right, I guess I will finish for today, and maybe I will continue next time with the fermionic algebra.